Hardware faults. When we think of causes of system failure, hardware faults quickly come to mind. Hard disks crash. RAM becomes faulty, the power grid has a blackout, someone unplugs the wrong network cable. Anyone who has worked with large data centers can tell you that these things happen all the time when you have a lot of machines. Hard disks are reported as having a mean time to failure MTTF of about 10 to 50 years. Thus, on a storage cluster with 10,000 disks, we should expect on average one disk to die per day. Our first response is usually to add redundancy to the individual hardware components in order to reduce the failure rate of the system. Disks may be set up in a RAID configuration, servers may have dual power supplies and hot swappable CPUs, and data centers may have batteries and diesel generators for backup power. When one component dies, the redundant component can take its place while the broken component is replaced. This approach cannot completely prevent hardware problems from causing failures, but it is well understood and can often keep a machine running uninterrupted for years. Defined in Approaches for Coping with Load on page 17. Until recently, redundancy of hardware components was sufficient for most applications, since it makes total failure of a single machine fairly rare. As long as you can restore a backup onto a new machine fairly quickly, the downtime in case of failure is not catastrophic in most applications. Thus, multi-machine redundancy was only required by a small number of applications for which high availability was absolutely essential. However, as data volumes and applications computing demands have increased, more applications have begun using larger numbers of machines, which proportionally increases the rate of hardware faults. Moreover, in some cloud platforms such as Amazon Web Services (AWS), it is fairly common for virtual machine instances to become unavailable without warning, as the platforms are designed to prioritize flexibility and elasticity over single machine reliability. Hence, there is a move toward systems that can tolerate the loss of entire machines by using software fault tolerance techniques in preference or in addition to hardware redundancy. Such systems also have operational advantages. A single server system requires planned downtime if you need to reboot the machine to apply operating system security patches, for example, whereas a system that can tolerate machine failure can be patched one node at a time, without downtime of the entire system. A rolling upgrade. See Chapter 4. Software errors. We usually think of hardware faults as being random and independent from each other. One machine's disk failing does not imply that another machine's disk is going to fail. There may be weak correlations, for example due to a common cause, such as the temperature in the server rack, but otherwise it is unlikely that a large number of hardware components will fail at the same time. Another class of fault is a systematic error within the system. Such faults are harder to anticipate, and because they are correlated across nodes, they tend to cause many more system failures than uncorrelated hardware faults. Examples include a software bug that causes every instance of an application server to crash when given a particular bad input. For example, consider the leap second on June 30, 2012, that caused many applications to hang simultaneously due to a bug in the Linux kernel, a runaway process that uses up some shared resource CPU time, memory, disk space, or network bandwidth. A service that the system depends on that slows down, becomes unresponsive, or starts returning corrupted responses. Cascading failures, where a small fault in one component triggers a fault in another component, which in turn triggers further faults. The bugs that cause these kinds of software faults often lie dormant for a long time, until they are triggered by an unusual set of circumstances. In those circumstances, it is revealed that the software is making some kind of assumption about its environment, and while that assumption is usually true, it eventually stops being true for some reason. There is no quick solution to the problem of systematic faults in software. Lots of small things can help. Carefully thinking about assumptions and interactions in the system, thorough testing, process isolation, allowing processes to crash and restart, measuring, monitoring, and analyzing system behavior in production. If a system is expected to provide some guarantee, for example, in a message queue, that the number of incoming messages equals the number of outgoing messages, it can constantly check itself while it is running and raise an alert if a discrepancy is found. Human errors. Humans design and build software systems, and the operators who keep the systems running are also human. Even when they have the best intentions, humans are known to be unreliable. For example, one study of large internet services found that configuration errors by operators were the leading cause of outages, whereas hardware faults, servers, or network played a role in only 10-25% of outages. How do we make our systems reliable, in spite of unreliable humans? The best systems combine several approaches. Design systems in a way that minimizes opportunities for error. For example, well-designed abstractions, APIs, and admin interfaces make it easy to do the right thing and discourage the wrong thing. However, if the interfaces are too restrictive, people will work around them, negating their benefit. So this is a tricky balance to get right. Decouple the places where people make the most mistakes from the places where they can cause failures. In particular, provide fully featured non-production sandbox environments where people can explore and experiment safely, using real data, without affecting real users. Test thoroughly at all levels, from unit tests to whole system integration tests and manual tests. Automated testing is widely used, well understood, and especially valuable for covering corner cases that rarely arise in normal operation. Allow quick and easy recovery from human errors to minimize the impact in the case of a failure. For example, make it fast to roll back configuration changes. Roll out new code gradually so that any unexpected bugs affect only a small subset of users, and provide tools to recompute data in case it turns out that the old computation was incorrect. Set up detailed and clear monitoring, such as performance metrics and error rates. In other engineering disciplines, this is referred to as telemetry. Once a rocket has left the ground, telemetry is essential for tracking what is happening and for understanding failures. Monitoring can show us early warning signals and allow us to check whether any assumptions or constraints are being violated. When a problem occurs, metrics can be invaluable in diagnosing the issue. Implement good management practices and training, a complex and important aspect, and beyond the scope of this book. How important is reliability? Reliability is not just for nuclear power stations and air traffic control software. More mundane applications are also expected to work reliably. Bugs in business applications cause lost productivity and legal risks if figures are reported incorrectly, and outages of e-commerce sites can have huge costs in terms of lost revenue and damage to reputation. Even in non-critical applications, we have a responsibility to our users. Consider a parent who stores all their pictures and videos of their children in your photo application. How would they feel if that database was suddenly corrupted? Would they know how to restore it from a backup? There are situations in which we may choose to sacrifice reliability in order to reduce development cost. For example, when developing a prototype product for an unproven market, or operational cost, for example, for a service with a very narrow profit margin. But we should be very conscious of when we are cutting corners. Scalability. Even if a system is working reliably today, that doesn't mean it will necessarily work reliably in the future. One common reason for degradation is increased load. Perhaps the system has grown from 10,000 concurrent users to 100,000 concurrent users, or from 1 million to 10 million. Perhaps it is processing much larger volumes of data than it did before. Scalability is the term we use to describe a system's ability to cope with increased load. Note, however, that it is not a one-dimensional label that we can attach to a system. It is meaningless to say X is scalable or Y doesn't scale. Rather, discussing Roman 2, a term borrowed from electronic engineering, where it describes the number of logic gate inputs that are attached to another gate's output. The output needs to supply enough current to drive all the attached inputs. In transaction processing systems, we use it to describe the number of requests to other services that we need to make in order to serve one incoming request. Scalability means considering questions like, if the system grows in a particular way, what are our options for coping with the growth? And how can we add computing resources to handle the additional load? Describing load. First, we need to succinctly describe the current load on the system. Only then can we discuss growth questions. What happens if our load doubles? Load can be described with a few numbers which we call load parameters. The best choice of parameters depends on the architecture of your system. It may be requests per second to a web server, the ratio of reads to writes in a database, the number of simultaneously active users in a chat room, the hit rate on a cache, or something else. Perhaps the average case is what matters for you, or perhaps your bottleneck is dominated by a small number of extreme cases. To make this idea more concrete, let's consider Twitter as an example, using data published in November 2012. Two of Twitter's main operations are Post-tweet, a user can publish a new message to their followers. 4.6K requests/sec on average, over 12K requests/sec at peak. Home timeline, a user can view tweets posted by the people they follow. 300K requests/sec. Simply handling 12,000 writes per second. The peak rate for posting tweets would be fairly easy. However, Twitter's scaling challenge is not primarily due to tweet volume, but due to fanoutility. Each user follows many people, and each user is followed by many people. There are broadly two ways of implementing these two operations. Posting a tweet simply inserts the new tweet into a global collection of tweets. When a user requests their home timeline, look up all the people they follow, find all the tweets for each of those users, and merge them sorted by time. In a relational database like in Figure 1-2, you could write a query such as maintain a cache for each user's home timeline, like a mailbox of tweets for each recipient user. See Figure 1-3. When a user posts a tweet, look up all the people who follow that user, and insert the new tweet into each of their home timeline caches. The request to read the home timeline is then cheap, because its result has been computed ahead of time. Figure 1-2. Simple relational schema for implementing a Twitter home timeline. Figure 1-3. Twitter's data pipeline for delivering tweets to followers, with load parameters as of November 2012-16. The first version of Twitter used Approach 1, but the system struggled to keep up with the load of home timeline queries, so the company switched to Approach. This works better because the average rate of published tweets is almost 2 orders of magnitude lower than the rate of home timeline reads, and so in this case it's preferable to do more work at write time and less at read time. However, the downside of Approach 2 is that posting a tweet now requires a lot of extra work. On average, a tweet is delivered to about 75 followers, so 4.6K tweets per second become 345K writes per second to the home timeline caches. But this average hides the fact that the number of followers per user varies wildly, and some users, in an ideal world, the running time of a batch job is the size of the dataset divided by the throughput. In practice, the running time is often longer, due to skew data not being spread evenly across worker processes and needing to wait for the slowest task to complete. Have over 30 million followers. This means that a single tweet may result in over 30 million writes to home timelines. Doing this in a timely manner, Twitter tries to deliver tweets to followers within 5 seconds, is a significant challenge. In the example of Twitter, the distribution of followers per user may be weighted by how often those users tweet, is a key load parameter for discussing scalability, since it determines the fanout load. Your application may have very different characteristics, but you can apply similar principles to reasoning about its load. The final twist of the Twitter anecdote. Now that Approach 2 is robustly implemented, Twitter is moving to a hybrid of both approaches. Most users' tweets continue to be fanned out to home timelines at the time when they are posted, but a small number of users with a very large number of followers, i.e. celebrities, are accepted from this fanout. Tweets from any celebrities that a user may follow are fetched separately and merged with that user's home timeline when it is read. Like an Approach, this hybrid approach is able to deliver consistently good performance. We will revisit this example in Chapter 12 after we have covered some more technical ground.